Today's lesson is on approximating areas with Riemann sums. So we're going to look at 4 different ways to approximate areas under curves. And we're going to use the same function for all 4 examples. So all 4 examples, we are going to graph f of x equals 6x minus x squared. And I'm going to label my graphs like this. This just kind of helps get a good picture of the graph. So I am skipping a unit, so 2 units over is actually 1 unit. But then on the y-axis, every unit is 1. Okay, so to graph this function, I've got the point 0, 0, and 6, 0, and the axis of symmetry vertex is at 3, 9. I've got 1, 5, 2, 8, 4, 8, 5, 5. Okay, so I've got this parabola that opens down. And we're going to use the same example for all 4 of our examples today. Okay, so we're looking to find the area under this curve. And we're going to look on the interval from 0 to 6. So from 0 all the way to 6. And we're going to use 6 intervals. So this is easy to figure out how we're going to create these rectangles. There'll be 1, 2, 3, 4, 5, 6 rectangles. And because it's a left Riemann sum, what we're going to do is start on the left of our graph and kind of move over to create the width. So at 0, I'm starting here and I'm going over. So there's no height to this first rectangle. And then at 1, I'm going to put a point on the graph on the left, and then I'm moving over to the right. So there's my first rectangle. And then at 2, I get a point and I go over. At 3, 4, and 5. So as you can see, if I find the area of these rectangles, I'll have an approximate area under this curve. So here's some missing area here, but then I kind of make up for it over here. Missing here, but I'm making up for it over here. So it should be a pretty good estimate. Now, this is a pretty easy one where we can clearly see the dimensions of these rectangles, find the area, and add them up. But I'm going to write this out in kind of the technical format. How would we get the dimensions of this rectangle? The height is coming from this point. So the height of this rectangle is the function at 1, would give us that y value, that's the height. And then the width is our change in x, which in this case is just 1. So we're always doing the y value, getting from the function, multiplying by the change in our x. Okay, so in this case, we're actually starting here. So this is f of 0 times our change, and in this case is 1. I'm going to write out the 1 just so we have this visual, plus f of 1 times 1, plus f of 2 times 1, plus f of 3 times 1, plus f of 4 times 1, plus f of 5 times 1. And notice how I don't do an f of 6 because it's a left Riemann sum. That would be over here. So f of 5 times 1 is our last one. So if they all have this change in x, what I can do is you factor that out. So in this case, it's silly because it is just 1. I just want you to see the process. So we factored out the change in x, and then 0 to 6 was the interval, but it was a left Riemann sum. So we're starting with 0, but we're ending at 1 less than that. So let's actually get our function values on here. So 1 times f of 0 is 0, f of 1 is 5, f of 2 is 8, 9, 8, and 5. And you should get that that equals 35 units squared. So that is the estimate for area under the curve. Okay, next example, like I said, we're using the same function every time, so I already sketched it on there. And this time we're doing a right Riemann sum, and I've changed the domain so from 1 to 4. So we're only going from 1 to 4, but I still have that we want to divide it into 6 different intervals. So to do that, we're going to look at these half intervals. Okay, so now we're doing a right Riemann sum. So I'm going to start on the right side of my interval right at 4. I'm going to put a dot, and I'm going to move to the left. Okay, so at 3.5, I will put a dot and move over, putting the dot on the right, moving to the left. So at 3, moving over, 3.5, 2, 1.5, and then done. So this time I'm not estimating the entire area, it's just from 1 to 4. So let's again think about where the dimensions of the rectangle is coming from. The width of every rectangle is this change in x, which in this case is 1/2. And then the height, so the height is coming from these function values. So even though, so the interval starting at 1, my first y value is at the 1.5. So let's write it all out. So f of 1.5 times the change in x 1/2 plus f of 2 times 1/2 plus f of 2.5 times 1/2 plus f of 3 times 1/2 plus f of 3.5 times 1/2, so this is a big one, plus f of 4 times 1/2. So notice right Riemann sum, so from 1 to 4, I have the ending on the right, but I'm not starting with, oh, this was supposed to say 1.5, 1.5, 1.5, so I'm not starting at 1, I'm starting at 1.5. And every term has that 1/2 in common that can be factored out. So really you can go straight to this step and not have to write this first step. I just kind of like to show you both so you get the hang of it and can see where it is all coming from. So now let's evaluate all of these. So I have 1/2 and I'm going to help you out. So f of 1.5 is 6.75. And then I've got 8, and then 8.75, whoops, 9, and 8.75 again, and 8. So if you calculate all of that, you will get that the area on that interval is about 24.625 units squared. Here we go, example number 3, same function. So I've already graphed it, and I'm dealing with now a midpoint Riemann sum. We're going to estimate the area from 0 to 6, and this time our intervals are only going to be, we're going to look at just 3 of them. So how will we draw our rectangle? Well, first our intervals, if we're only going to have 3 of them, then each interval will have a width of 2. So midpoint is exactly what you would think. What is the middle of this interval? It's at 1, and we're going to go to the right and to the left like this. Okay, so from the interval 2 to 4, the middle of that interval is 3, and then we'll go left and right, and then the middle of the last interval is at 5. So finding the dimensions of our rectangles, change in x this time is 2, and then our function values are at f of 1, f of 3, and f of 5. That's the height of our rectangles. So we always factor the change in x out in front. So this time let's just start with that. Let's have 2 out in front, and then in parentheses we will have our 3 function values, f of 1 plus f of 3 plus f of 5. So this time I'm skipping that first step. So 2, and then I'm going to have 5 plus 9 plus 5. And this will come out to about 38 units squared. And now for our final example. Same function, already graphed it. Now we're using a trapezoidal sum. And we're looking at the interval from 1 to 5, and then 4 intervals. So this will be an easy one where we're just looking at change in x being 1. But we're going to create trapezoids. So trapezoid, if I, instead of a rectangle, if I go up here to this point and this point, and then connect them on this diagonal, hey, that looks like it's going to be a good estimate. Okay, so now f of 3 and f of 2, connect them. F of 4 and f of 3, and then f of 5 and f of 4. So it's probably been a while since you've had to calculate area of a trapezoid. So I kind of just drew what our trapezoids look like off to the side. And the parallel sides, those are your bases. So base 1 and then base 2. And then our change in x is actually the height of the trapezoid. And then area of a trapezoid is 1/2. And then base 1 plus base 2 times the height. And then if you think about on the graph, so the height is the change in x, and in this case the change in x is just 1 every time. And then, so from our very first trapezoid here, base 1 would be f of 1, and base 2 we're going to get from f of 2. So the area of that first trapezoid is 1/2 f of 1 plus f of 2 times the height, which is 1. So I know it's silly to write the 1, but we're going to, so you see everything. Okay, so that's the first one. So now the second one is 1/2. It's f of 2 plus f of 3 times the change in x, 1, plus 1/2 times f of 3 plus f of 4 times 1, plus 1/2 times f of 4 plus f of 5 times 1. Okay, so what does every term have in common? They all have a 1/2, and they all have that change in x, which is 1. So we can factor out those out in front. And then what are you left with? Well, notice how you have the 1 f of 1, but you have 2 f of 2's. And then you also have 2 f of 3. And 2 f of 4. And only 1 f of 5. So let's get in our value. So 1/2 times f of 1 is 5, plus 2 times f of 2 is 8, plus 2 times f of 3, 9, plus 2 times f of 4 is 8 again, and plus a single f of 5, which is 5. So if you calculate all of that, you will get that the area is about 30 units squared. So there is your full video on approximating areas under the curve with Riemann sums. Apologies for it being a long video, but it was a lot of good information, so good luck.